Welcome. It is 4:45. You are all the diehards. Thank you for coming. You're hopefully here for improving Columnstore load scalability in large servers. Keep your cell phone silenced. Explore everything PASS has to offer. And my take on this slide, as you've heard so many, is make each and every session that you go to valuable for you. I'm going to do my best to make this session valuable, but if you have any questions, please ask them. I've got a few breaks in this presentation for questions, so if you can wait until then. I've got 185 slides, so I do need to keep things going. Oh, you don't like that, huh? It'll be over before you know it. My name is Joe Obbish. I am a developer, sometimes accidental DBA, sometimes troublemaker, sometimes architect, all kinds of things. Here are my SQL Server credentials. They're OK, I guess, but you can trust me. I promise to read all of your feedback, good or bad, so help me out. I'll read it all, and you can win prizes. I don't know what they are. I'm sure they're great. So scalability can be used in a few different ways. The way that we use it is, as the server gets bigger, we want to be able to do more work within the SQL Server. And you can measure the scaling factor with servers of different sizes and seeing how much work each different hardware configuration can do. So a really simple example, if I've got a 10-core server, I'm doing 100,000 transactions per second. Ideally, I'm going to get linear scalability. So if I scale all the way up to 100 cores, I could do 1 million transactions per second. I've got 112 cores personally, a little under a terabyte of RAM, SAN storage, which I'm told is pretty good. It's virtualized, unfortunately, and the database recovery model is simple. I've got a little over 1 billion rows in 112 different tables, 300 gigabytes of staging data in total, and I've got one target table for all of that data. It's got a clustered column store, but I've got only 6 minutes to load that data. They say that your nightly ETL times get shorter and shorter, right? So 6 minutes, that's the goal. Anyone loading all their data in 6 minutes? You've come to the right place then. Oh, you?
Is your data in the 100 tables because you want it to be, or did you put it that way to help?
My data is in 112 tables because I have 112 different data sources. But in reality, it's to help me out. So there are 2 different ways of loading Columnstore. You can load it with max.1 insert queries and run many queries at a time. Or you can have a single parallel query with max.1 greater than 1. And the max.1 load strategy with many concurrent sessions is the most scalable if it can work with your data. And through the power of demos, I've got 112 cores, 112 tables. That's 1-to-1. So that's the real reason why. You've kind of taken the magic away, but that's all right. OK, so I read the internet. If you're doing a lot of DML, you want to use batches. You don't want to have big, long transactions. That's the best thing to do. So that's what I'm going to do. I have a simple sort procedure. It reads my staging table, inserts 100,000 rows at a time. I'm going to have 112 of those running at once. 15,887 seconds to load my data. I was hoping for a load time that made sense in seconds, and I didn't quite get one. This is about 4.4 hours. That's a little longer than 6 minutes, right? OK, I've got a lot of work to do here. So when I'm faced with a scalability problem or performance issue, I generally look at the same things in the same order. And I'm not going to say that this is the best way of doing it. It's kind of my starting point, and then I adjust as needed. So let's just go through them all. Number 1 for me, check throughput. You need to know how much real work you're doing per unit of time. So make sure that you can do this. Sometimes you can use perfmon, sometimes the application will log what you need. Just make sure you're able to do this. Because CPU doesn't make sense without this context. So that's number 2. CPU, compare your CPU to how much work you're doing. You can figure out a lot of things that way. I found that perfmon is the most reliable way to, well, the man in the hat told me that perfmon is the most reliable way measuring CPU. If you're watching the workload live, you can use resource governor. This is also measurable within SQL Server, even without resource governor, but it can be inaccurate at times. We'll go through that. For nightly ETL loads, let's say we're loading data at 3 a.m., we've got no end users, you've got a scalability problem. One of my truths is it's always a CPU problem. If my workload is too slow and CPU is too high, I'm using too much CPU. I need to make my code more efficient. I need to use less CPU so I can shrink my workload. If my CPU is too low, I've got a different type of CPU problem, not using enough. And if I want to use full advantage of my hardware, I need each and every CPU core to do useful work, and ideally, each and every CPU core is working at 100%. That's only because I'm loading data in the middle of the night, there's no end users, I've got hardware, might as well use it. If you can't use all your hardware, then you can't be scalable. So after that, you can look at some of the typical ways of viewing contention in SQL Server, waits, latches, and spin locks. This can be very simple. I just have an agent job that logs data every minute or so. The important thing here is you need to be able to look during the period of your workload. If you started your server 3 months ago and you're looking at waits from 3 months ago till today, that might not be very helpful. And waits are just numbers. Throughput is what matters. If your throughput's good enough, then who cares about the waits, right? Also, don't be afraid of waits. If you've got a really interesting workload and you're pushing your server as hard as you can, you're going to have some waits. That's OK. What if you have no waits? So most of the time, the server's bored. It's got nothing to do. It's got little to do. Or maybe you're very, very good at your job, in which case I might not be able to teach you a lot. You might have come to the wrong session. Or maybe you're very lucky. I don't view myself as a lucky person. I ran my workload. It took 15,000 seconds. I wanted it to take 360. So that's why I know how to present all this stuff. Let's say all that stuff doesn't work. I look at waits and latches and spin locks. I still don't know what to do. You can get more creative. So you can use extended events to get a fire hose of useful or not useful data. You can do something called ETW tracing, and that will tell you within the OS where are we spending CPU on which call stacks. And that can give you useful hints as to where the problem could be. If you're really adventurous, you can fire up the debugger, attach it to SQL Server, and try to figure out what's going on that way. And I've got a blog post where I walk through a similar example of doing this type of creative work. So we talked about a way to attack scalability problems, but didn't talk about Columnstore. That's because this is kind of a generic method or checklist in terms of attacking scalability problems. So let's use what we just talked about to get our workload faster than 15,000 seconds, because that's kind of embarrassing, right? I'm very embarrassed right now. So here's a sample of CPU from perfmon. There actually is, I can't really point, but there really is a red CPU line here. CPU is at about 1%. So I've got a CPU problem, right? CPU is too low. I need to use more CPU. OK? So let's take a look at our wait stats for the workload. If you do the math, I get about 75 seconds of sleep task wait per second. And I've got 112 running sessions. So this is my number. This is my problem by an order of magnitude. Now, you might see some guidance, well, sleep task is benign, filter it out, and most of the time you can, except when you can't. So here, I've got low throughput, I've got low CPU, I've got a very high sleep task weights. I need to look into it. This is not benign. Now, sleep task is kind of a generic holder for lots of different types of weights, so I need to look a little bit deeper. We can use extended events. So extended events have an option to capture a call stack when the event fires. And when you run into like weights or latches or spin locks you've never heard of, and no one's ever blogged about, not that I've ever been there, you can use extended events to get a hint as to what's going on. This requires traceflag 3656 in all versions to get call stack resolution. It also needs traceflag 2592 starting in SQL Server 2019, which is now documented. You're welcome for that. And the earliest example that was published for this, there's a classic white paper, Resolving Spin Lock Contention on SQL Server 2008. I read it every day. It's great. Now, it's about spin locks, but the same technique applies to weights too. So here's an extended event session. You can try it at home. The important points here are the weight type of a 108. That's sleep task on this version of SQL Server. Then we've got the target of histogram with the call stack. So I'm going to get like hundreds of millions or billions of events firing here. I want to look at only the most popular call stacks. And this is a way to have SQL Server summarize that for me. So I fire up my workload with this extended event turned on. And here's the most popular call stack. So call stacks are a bit tricky. You have to read from the bottom up. They require internals knowledge or a friend at Microsoft or whatever your best theory is. So I'm going to read through this a bit. Okay, I'm getting a row from a scan. I need to update a row in a Columnstore. That turns into an insert. I'm inserting a small record. I need to get a lock, and then it sleeps. So during my Columnstore inserts, I'm hitting this lock that it seems like I can't get, and then the worker sleeps. So this is hinting that there's some problem with the Columnstore insert operator itself. So I'm going to look at the query plan and see if there's anything suspicious. Like I just said. And there is. I'm inserting 100,000 rows. My estimate is 13 rows. Well, that's suspicious, right? That's not right. So why did this happen? Parameter sniffing. I use parameterized SQL like a good developer. I'm looping over 100,000 rows at a time. My histogram wasn't very good around the edges. So the first estimate was 13. The estimate gets cached and it gets reused. And you might be wondering, well, why does this matter? Like, this has the plan shape you want. You're just reading from a table and doing an insert. Who cares about the estimate? Except SQL Server with Columnstore will not ask for a memory grant if your estimate is less than 251 rows. It will write to delta row groups instead of writing to compressed row groups directly. So when you insert data into a table, SQL Server, the engine makes a choice about which algorithm it uses to actually do that insert. So if you've ever seen cases where you expected a minimal logging and you didn't get it, for example, the most popular reason for that is the cardinality estimate is too low. SQL Server picks an algorithm that doesn't qualify for minimal logging, and then you don't get that. So with Columnstore, SQL Server has different algorithms that it can pick from. It thinks the estimate's very low. It picks an algorithm designed for a very small estimate, and then that's not what's happening. So we get very bad performance, we get very bad scalability. We've tricked SQL Server into doing the wrong thing. Now, none of this is exposed in the plan typically. This is just what can happen. I'm going to fix my estimate. I'm going to give SQL Server better information, then it'll do the right thing, right? That's how it always works. OK, we're at about an hour now. That's far off from 6 minutes, but we're making progress. SQL Server says CPU is about 61%. So it sounds like I'm using too much CPU now. Except Perfmon strongly disagrees. Perfmon says we're at about 10% CPU. So who are you going to trust? SQL Server or Perfmon? Oh yeah, of course you're going to trust Perfmon. So why can this happen? There are some wait types that are counted as CPU busy but within SQL Server. So consider an external wait type. SQL OS hands off control of the code to the OS that's hosting it. The OS does some kind of work, then it returns control back to SQL OS. SQL OS itself has no idea what's going on in the OS at that time. So from their accounting, they just assume that it's going to be CPU busy within the OS, and it isn't always. That's one reason you can see these large mismatches between what SQL Server thinks is happening and what's really happening. Take a look at our weights, because we've got a CPU problem. It's too low. There's this reserved memory allocation EXT weight. The EXT stands for external. So OK, I kind of get now why my CPU is reported differently. But I've never heard of this weight. No idea what it is. I Googled for it, found nothing. OK? But resource semaphore, I've heard of that one. So I'm going to ignore my top weight. I'm going to attack the weight type that I know about. So why is this happening? Query wants a memory grant. It can't get it. I hate seeing this weight. If you want my point of view, I suppose you do, because all of you came here. If you ever see this weight, you fix it. And you do the math on this, I get about 15 seconds of this weight per second. You can view this during the workload by checking out this DMV. All of the nulls are queries which could execute but can't because they're running out of memory grant. So why did this happen? This happened because I had a VM problem. Max server memory was set way too low. SQL Server didn't have enough memory to support my concurrency. Queries ended up waiting. OK? This might happen for other reasons too. So when SQL Server is doing Columnstore inserts, it has to estimate the memory grant needed. That's based off of the data types and a few other things. Those estimates can be significantly more than is actually needed. But here, I've just got a configuration problem. So I'm going to raise max server memory to see if that helps. It did help. We're at about half an hour now. SQL Server thinks CPU is very high. It's not. Still at about 10% CPU. I've got this 112-core server, and I'm using 10 cores. It's not very scalable. OK? Look at weights again. So sleep task is down. That's good. I've got this reserved memory allocation EXT weight. I still don't know what that is. Am I going to have to face it? Not yet. So even though this weight event is so high, if we look at the Columnstore table, it's not compressed yet. It's all in delta row groups. So what happens here? If you insert fewer than 102,400 rows, SQL Server goes to a delta row group, which is a uncompressed clustered index. So I've got a billion rows. That's in reality, it's kind of a heap. So my data isn't compressed. So I insert rows into the table, but this isn't going to be useful for anyone. OK. So the maximum number of rows per row group, it's 1048576, about 1 million rows. I'm going to increase my batch size to that maximum number of rows that can fit in a row group. That's a trick people sometimes use. I want to bypass the delta row groups. I want to insert directly into compressed data. It's a little better, not by much. But now I've got compressed data here, right? So this is the first good result. OK, I want to load my data in 6 minutes. It's taking about half an hour. That's 5 times too long. I've got a compressed table though, made some progress. Any questions? I should be able to take a few. I've only got about 130 slides to go. I'm doing a great job and there are no questions. Okay, good. I'm gonna look at CPU for my workload. Okay, it's above 10%. It's not very stable though. It's not using it, and I want this to be higher. I want to use all my server's resources and I'm not. So I've got a CPU problem, it's still too low. Our enemy returns, the reserved memory allocation ext weight. It's number one weight by far. Okay, I'm gonna have to deal with this now. That's fine. You do the math, 54 wait seconds per second. And then investigate this using ETW tracing. You could use extended events here too, but I'm just using this to show you a little bit of a different technique. So I fire up my workload, fire up the recorder, I analyze data for a while, and I know something called memory clerk internal allocate reserve pages and memory node allocate reserve pages. There's some contention here. That sounds suspiciously like reserve memory allocation ext, right? So based on the name, based on some of these call stacks, I suspect the contention is caused by we want to reserve or we want to allocate memory pages. That's the problem. There are some debug extended events, page allocated, and page freed. So these fire once for every memory page that's allocated and once for every memory page that's freed. That happens very frequently, so you may not want to do this in production. You can filter results down. So in this case, by process of elimination, it's the SQL QE reservations memory clerk. Again, there's that reserved word. Okay, so I'm going to only, all right, here's the example to try at home, not in production. I'm going to do a really small test because that's going to be a lot of overhead. I'm going to insert 1 million rows twice and 2 different inserts. And if you do the math and scale it up to 1 billion rows, you need to allocate about 6.3 terabytes of memory and free 6.3 terabytes of memory. It kind of sounds like a lot, right? Or if you're going to contend over something, if you've got 6.3 terabytes of it, well, I can see why there might be contention. So this graph is a running total of all of the allocated pages, and then we're subtracting a running total of all of the freed pages. So this is to get an idea of how much memory is currently allocated to the query. You can see a pattern here, right? So we're at the start of the first insert. We're reading data into the buffers. We start compression, memory peaks. We keep doing compression. We write the data to disk. We zero out memory. We do it all over again. That makes sense? There's 2 peaks. There's 2 inserts of 1 million rows. So after each insert, I free all of the memory pages used for compression. So maybe if I insert more than 1 million rows at a time, SQL Server can reuse some of those memory pages. And instead of allocating 6.3 terabytes total, I will reduce that number. And if that's what I'm contending on, then that can reduce the weight. So I'm going to simplify my start procedure that loads data. I'm going to read all the data from each table, do 1 insert for each table, no batching. Batching has caused nothing but problems for me. Okay, it's a little faster. Knocked off a few minutes. 1,600 seconds. CPU spikes a bit higher, but it's very unstable. I'm not using enough CPU. I still have a CPU problem, not enough CPU. It's gotten better, right? there's less waiting, but I still have this reserved memory allocation ext wait. I also wish that Microsoft made the name shorter. Just repeating reserved memory allocation ext wait over and over again. That's okay. Do the math. 34.7 seconds of this wait type per second. Got a few other waits, not quite as bad. Still have the same bottleneck as before. Well, we can use extended events to see if our theory works out. I'm going to do the same graph as before. So this is an insert of about 9 million rows. And you can see a peak for each row group that gets compressed. Now, the important thing here, which I'd like to point out to you, but I kind of can, right? This doesn't zero out anymore. So after each row group is compressed and written to disk, we don't free all the memory. We're able to reuse some of it. So if I do the math with this approach for the full workload, I'm at only about 2.5 terabytes of total memory I'm freeing and allocating. That's why the wait event goes down. I've changed how I insert data. SQL Server is able to use less memory. The wait goes down. But that's still my #1 problem. So what else can I do? So I've got some kind of contention around memory allocation. Is there any configuration change I could do that might help as an experiment? I'm willing to try anything. How about lock pages in memory? It has memory in the name, right? And the reason this might actually work is lock pages in memory does more than control behavior under memory pressure. It actually uses different Windows APIs to allocate and free pages. Maybe those APIs are better, maybe they're worse. I'll try anything. So we enable lock pages in memory. Look at that. 812 seconds. Still not fast enough, but much better, right? SQL Server says CPU over the workload about 45%. Perfmon says CPU started out much better, then CPU drops over time. So they're mostly in agreement now. I still got a CPU problem. Workload's still too slow. Look at that. Our enemy is all the way down to 4th. Great. Page latch up. I've heard of that one before, right? We've all heard of page latch up. OK. So we've reduced one bottleneck. A new bottleneck rises to the top. Now you see why I have so many slides, right? So why did it help? First, we're going to look into why it helped. I know this is too small to read. You can read this at home. On the left, I've got the call stacks for lock pages in memory. On the right, I've got it for conventional. They're different, I promise. So for lock pages, there's this allocate user physical pages function that's in use. And for conventional, there's this NT allocate virtual memory function that's in use. For whatever reason, this one is a much better fit for Columnstore workloads in my experience. If I'm using Columnstore, I always want lock pages in memory turned on. OK, back to the bottleneck. We got some page latch up issues now. You can see this during the workload with SPWho is active or some other tools. So the first thing, in case you don't know what this wait type is, it's usually about allocation on the special pages. So PFS pages, SCAM, and so on. And most of the time, it's a TempDB. But if you have an extreme workload, you can see it in user databases. We've got an extreme workload. We're pushing the server so hard, we're getting a rare bottleneck. I use extended events to trace where the wait events are happening, and it is indeed the PFS pages on a user database. So why is this happening? I've got my database backed up by 2 LUNs, so I created 2 data files. And the way PFS allocation works is there's one so-called active PFS page per data file. So I've got 112 workers all contending over 2 PFS pages. Now, why is this a problem for Columnstore? Might be helpful to to do some testing, use some more extended events, get an idea of what's going on. So I'm going to have an event fire for every PFS latch. Again, be careful with this in production. Loading a million rows, same type of data I'm loading both times. First test is into a heap. Second test is into a column store. So the column store takes about, what is that, like 40% more latches or so. But the column store insert is much faster. I'm almost at 116,000 exclusive or update latches per second. And if you've got 112 sessions all running at maximum scalability, it's about 12 million exclusive and update latches per second. Latch acquirers are fast, but they're not that fast. That is what causes this contention. So I've got a 6-minute load period. I don't have time to play around. I'm going to go right to 112 data files for my database. Hey, I mean, it's the administrator's thing to deal with, not mine. It's fine. OK, it's a bit faster, 700 seconds. SQL Server says CPU is about 54%. You know, if I doubled my CPU, I'd be at about 6 minutes, right? So maybe this is actually possible, right? Maybe. That CPU graph looks pretty good at the start. I'm at about 90%. Got some dips I don't really like. But then there's this tail here where CPU is about 10%, and the workload keeps running. So things start out great, then they're not so great. It's back. The reserved memory allocation ext weight is back. So I've significantly reduced my page latch up, but it's still there. I've got 112 data files, but I still have this weight. I don't want this. I want this weight to be gone, OK? So why is this happening? Got more SOS schedule yield than before. I've got 32 seconds of signal wait, which doesn't sound like a lot. But when you use even more extended events to try to get an idea of the pattern here, so here's the pattern I often see. One worker enters a signal wait. The signal wait is equivalent to the resource wait. Other workers have a resource wait. First worker gets its latch, releases it. Then the other workers get and release their latch very quickly after that. So like, based on what's happening, it kind of seems like my signal wait gets amplified into more resource wait. OK? So I'm going to do an extremely brief overview of latch waits. One slide is all you need for latch waits, right? I want to modify a PFS page. I need an exclusive or an update latch. You can only have one of these at a time so that the memory page can be safely modified under concurrency. You don't want a worker overwriting data for other workers. If a worker can't get the latch it needs, it immediately suspends itself and waits. When that latch resource becomes available, the worker gets signaled. But if it can't immediately start executing its code again, it goes into the runnable state. And latch acquirers are they roughly respect first in, first out. So we've got some PowerPoint art here. On the left, you have one of our schedulers, scheduler 46. That has 2 user workers on it, worker 1 and worker 2. We've got all of our other schedulers, so 111 visible online schedulers in that cloud thing. We've got worker 3 currently acquiring an exclusive latch on page 5 in 511, which is a PFS page. So let's say worker 1 needs an exclusive latch while worker 3 is holding it. It can't get it. You can only have one latch on this page at once. It suspends itself. It enters a waiting state. It's waiting on that latch to be available. Worker 2 starts executing its code on the scheduler. Worker 3 releases the latch. Worker 1 is signaled. The latch resource it was waiting on is now available, but it can't run its code because worker 2 is running on the scheduler. So worker 1 is runnable. Worker 4 comes along. It wants an exclusive update latch. The page is available, but first in, first out. Worker 1 is owed the latch, so worker 4 suspends itself and waits. Worker 5 suspends itself. Worker 6, many other workers not on the slide. Worker 3. So I've got all of these waiting workers because worker 1 is owed the latch but can't get it. So after the longest 4 milliseconds of all our lives, worker 2 finishes executing its code. Worker 1 is now running its code. Worker 1 takes the latch for, what is it, like 1 microsecond or less than a microsecond or something. It gives it up. Now worker 4 can run. Now worker 5. Now worker 6. Now worker 3. Everybody's happy. There's no contention. So this is called a latch convoy. And this can happen when many processes need the same latch. The worst case for this, you can have over 100 workers all waiting, all being blocked because we have doubled up workers on a scheduler. And I've seen changes over 100 in production-like workloads. So that 4 milliseconds of signal wait time might seem insignificant, but it can be amplified by 100 times. You get really unlucky. If you've seen this optimized for sequential key feature, new in 2019, it solves a similar problem. So you can have latch convoys on the last page for a clustered index, and they use flow control to try to reduce this contention. Okay, you might be wondering, I have 112 sessions, I have 112 CPU cores. Why do I have doubled up workers, right? I should have 1 scheduler per session. So again, I'm going to explain scheduling in 2 slides instead of just 1. So when a connection is created, it gets assigned round robin to a soft NUMA node. The max stop work it does is always done on an assigned scheduler. The session cannot move out of its soft NUMA node. SQL Server tracks how busy schedulers are and does scheduler assignment based on that, but the scheduler assignment cannot change during a batch. And the frequency and robustness of this might not be as good as you might think or hope. So, well, why can this happen? I think I have soft NUMA nodes of 7 here. What if 8 connections go to 1 soft NUMA node? That means that 2 workers are going to get doubled up. Maybe there's a soft NUMA node that has busy internal processes that can get doubled up for that reason. Maybe you get unlucky. This can happen. This is especially bad news for our workload, because I've got long-running max-stop1 queries, which is especially sensitive. So if you think about it, let's say I have a query that has 300 seconds of work to do, max-stop1. If it gets doubled up on a scheduler, it has to fight for time on that scheduler. So if it only gets 50% CPU, it's going to take twice as long, which is why you see this tail. So when we're at 90% and you see that drop in CPU, these are all of the doubled up workers. So most of my sessions finish, but a few of them don't because they run for twice as long. And as a result, the workload takes longer. So what can we do about it? We can dust off our SQL Cat's Guide to Relational Engine. These great graphics. I don't know if this is a pyramid or something. I don't know what this is. It talks about large 64-core computers. Remember when 64 cores were large? So it's a little dated. But the essence of this strategy is, at the start of a session's work, it tries to reserve its scheduler in a shared table. If it's the only one on its scheduler, we execute the code. If it's not, we return an error code to the client. The client will retry that work until everyone is on their own scheduler. You can also do this with manual soft NUMA if you like editing the registry in production, and who doesn't, right? But I think there's a limit of 64 soft NUMA nodes, so it wouldn't work here. If you're a visual person, 112 CPUs, you can count them at home. The smiley faces are schedulers with no work to do, so they're kind of frowny faces from our point of view, but I couldn't find a frowny face in PowerPoint, so that's what we got. The red circle is schedulers that are doubled up or worse. So this isn't what we want. We want to be scalable. We want to use each and every CPU to its full capacity. This is no good. This is what we want. The transaction log writers always sit, well, for this type of server configuration, always be on schedulers 1 through 4. So if your transaction log writers are busy, this is about the best you can do in real life. So we're going to force each session to go to its own CPU. "504 seconds. Okay. It's looking a lot better, right? SQL Server says CPU is 87%. Perfmon seems to mostly agree. For the first time, we're at 100% CPU. That's what we want. So now we've got a new type of problem. We're using too much CPU. I'm going to look at my weights anyway, because, you know, some weights are CPU busy. And it's my biggest enemy, the reserved memory allocation EXD weight. Do the math, we're at about 17 wait seconds per second. Okay, so this is our problem. We can't go home. Boss says you have to load the data in 6 minutes before you can leave. What can we do? Are there more configuration options we can try? Trace lag 834, that has to do with memory. But Microsoft really tries to convince you to not use this trace lag, except in their own TPCH tests. But don't worry about that. So, can't use trace lag 834 in production with Columnstore. Severe errors, severe performance issues, blah, blah, blah. Okay, so can't do that. I bet some of you use and like Twitter. I don't. But on September 24th, 2008, the first good thing happened on Twitter. Slava from Microsoft revealed a trace flag, 876. So what does 876 do? So you remember those terabytes of memory page allocations? Those are all 8K allocations. Trace lag 876 for Columnstore compression uses 2 megabyte allocations instead. So I did a small scale test, insert 5 million rows with and without 876. So my number of allocations goes down by about 4. The number of pages allocated is significantly reduced because now I'm using 2 meg pages and not 8K. There's also much more, there's a less variance in the number of pages I'm allocated. Almost always I'm allocating 1 2 megabyte page at a time. This is worth a shot, right? So this trace lag is undocumented. So, some people will say, don't use in production. I'm desperate. I'm going to use it. I'm not allowed to go home. So I used it. OK, 434. Getting close. Target's 360. So I still can't go home. But I'm getting closer. SQL Server says 90% CPU. Here's what we've done so far. Making progress, right? This feels possible. that CPU graph would be perfect if the workload was fast enough, and it's not. So I'm using too much CPU. It's reduced. My number one bottleneck is less, but still reserve memory allocation ext. Okay? I'm going to measure my scalability because this weight just isn't going away. So I want to convince myself that this is possible. So I'm doing the same workload here. I'm just changing the number of concurrent sessions. And the middle column is the number of rows loaded per core per second. So the rate is much higher with 28 sessions. And my scaling factor is about 2/3. So if I had linear scalability, my workload would be much faster, and I'd be able to achieve my goal. So this is possible if I can scale better. Now I just have to do that, right? Any questions? I'm either doing a great job or everyone wants to leave on time. I'm not sure which one. So OneNote 876, it's undocumented. Microsoft isn't sure yet if they want to document it. They want more data from the community. So if you've got a large Columnstore workload and you can turn this on a test environment, please do so. Please send your data to Microsoft. The more data they have, then maybe they'll be able to support this for real, and then we can turn it on in production without any concerns. Yes?
What version of SQL are you running?
2017, some recent CU. And this trace log was added in a 2017 CU, maybe 13-ish, I'm not quite sure. It is not in SQL Server 2016. So 464 is pretty good. We have to get to 6 minutes. Okay, well, I mean, everyone got this book, right? SQL Server 2019 Unleashed. Look at all those pages. There's plenty of good stuff in here. So we could upgrade to SQL Server 2019. Maybe that'll help, right? It's test number 9, we upgrade. 405. Less than a minute away. Okay. Getting closer. Again, the CPU graph is pretty good. It's not perfect, except workload runs for too long. So I'm using too much CPU. Okay? My weights are down. Still got this reserved memory allocation ext weight. It's going to follow me to the grave, I'm pretty sure. Now, why might 2019 help? So this is all wrong. This is all deliberately wrong, actually. I'm going to open up my SQL Server 2019 book. I'm going to turn to page 385. I'm going to read from it. This improvement changes the way that concurrency is managed with PFS updates so that they can be updated under a shared latch rather than an exclusive latch. So there are no NDA violations in this session. I read from the book. I'm in the clear on that one. So that's just an example of how 2019 can help you with Columnstore workloads. You measure scalability in 2019, it's a little better, 0.71. I mean, that's pretty good for 112 cores, for 112 workers on 112 cores, but not good enough. Who thinks I can make it faster? Wow, that's it? Okay. I thought I'd get more hands on that one. Okay. So, I learned something as a presenter. Don't ask questions to your audience if you're not sure what the answer will be. Okay, not fast enough. What can be done? So all of you don't believe in me. I'm going to prove you wrong. What happened on August 3rd, 2006? I actually did some research on this. Couldn't really find anything interesting or notable. Apparently, a baseball home run for Barry Bonds was auctioned off. So if you're into baseball, that's cool, I guess. But that's not all that happened. Our friend Slava returns. He wrote a post on his weblog, because that's what we called it back then, or I was in high school, so I didn't call it that. But Slava talked about SQL Server 2005 scalability. And I mean, like, who can argue with this, right? SQL Server 2005, designed to scale. Now, the important quote, the hidden gem, which is findable only through like those internet cache sites. If you remove all global state, your scalability will be linear. To get your application to scale, remove completely, or at least partition global state your application's using. So what could that mean for us? I'm going to add a perfmon counter here. The total row groups compressed perfmon counter. And this screenshot starts at the beginning of the workload. So we can see for a long time, like about a minute, we don't compress any row groups. Then there's a large spike here. Then another spike. Then we're at about 112 row groups that are compressed at this point. So we've got a lot of different sessions all doing the same thing at once, right? They all start at the same time. They all do the same amount of work. You know, they read a million rows. They read it into the buffer. They apply vertipack. They apply encoding. They compress the data. They write it to disk. They need their row group flush lock. Then it happens all over again. So if you have 112 sessions all doing the same thing in SQL Server, there's opportunities for contention, and your scalability can go down. So what could we do to try and work around this? I'm going to change my server procedure that loads data. I'm going to throw a little bit of randomness in there. So instead of inserting 9 million rows at once, I'm going to do 2 inserts. And the size of the first insert is going to be very small, but it's going to vary in size. Like I might insert 500,000 rows for the first one, then the other 8.5 million for the next one. Or I might insert 750,000 rows, then the rest of the rows, or 150,000 or so on. So the point of this is, instead of every session reading 1 million rows and compressing 1 million rows, about 14% have a smaller row group, and 14% have a slightly bigger row group. So I can make my sessions do different things at different times. And if I'm doing that, I could have less contention. Does that make sense? So I try it. I vary the size of the initial insert, add some randomness to the mix. And for all the doubters out there, 346. Thank you. So we load our data in 6 minutes. CPU is great. There's that dip there. I don't know what happened there, but that CPU graph is nearly perfect. Got some weights. Interesting workloads are always going to have weights, but now it's fast enough. I don't have to care about reserved memory allocation ext anymore. It doesn't matter. It's the next guy's problem when it has to be run in 5 minutes, right? If I look at that same counter, now instead of long plateaus and jumps, it's much more stable over time. So I was able to like shift the work that each session is doing, and that significantly sped up the workload. And for this type of loading, the actual effect on row group quality and table size was very small. Now, I'm not saying you should actually randomly insert certain numbers of rows in production, but if you've got a more complicated ETL that takes longer than 6 minutes, you might have some queries that insert in a Columnstore and some that don't. If you can mix those up, you can improve your scalability. So instead of like saving all of your Columnstore inserts to the very end, if you can spread those out, that can help. Think about like if you have 1 worker spilling to tempdb, that might be OK. If you have 112 workers spilling to tempdb, that's going to be a problem. Same thing here, except a lot of this stuff just isn't exposed to us. Our scalability still isn't great, but hey, it's good enough. Our rates are good enough across the board. We're loading it in 6 minutes. We're using our hardware, finally. It only took 11 tests. How are we doing on time? Doing great on time, 20 minutes, because no one has any questions. Okay. I'm going to do a quick review here. You have a question. Let's hear it.
Are you sacrificing any performance in the data retrieval if you're going to select this data for all these changes you're making to the size of the numbers?
So the question was, are you sacrificing any performance by changing the amount of data that's loaded? I have clustered indexes on my staging tables, so in this case, I'm not. But if you had heaps, for example, then you might be doing that. Is that what you're asking?
Well, like in the Columnstore, right?
Okay.
If I'm loading like 500,000 into one
Mm-hmm.
set, that's maybe it's 200,000, as opposed to putting a million rows there in that vaccine.
Oh, I see. So you're talking about query performance when reading the data.
Yeah.
Okay, so the question was, if I'm deliberately creating undersized row groups, is that going to impact query performance when reading data from the table? It will to a degree, but like if you think about loading data in real life, like you're not going to have 1048, 576 rows all the time, right? Like you might have some leftover rows or dictionary pressure or memory pressure. So the way that I think about row group trimming is consider the whole table. Like consider your average row count, consider what kind of compression you're getting. And I've looked at this, and for our data, undersized row groups don't really seem to impact the compression rate. Now there are reasons that they can, so your mileage is going to vary, but like for this scenario, I think I get something like 10% more row groups, maybe less than that. So on the whole, it ends up not mattering here.
Do you think that in this situation, if you have implemented memory optimized table, it would have helped
Would that be for staging or for the Columnstore?
for the stage?
So the question was, if I implemented in-memory LTP for the staging table, would that have improved the rate of data of my load, right? So here, I've got about 5.5 gigabytes of IO throughput and 300 gigs of data and 6 minutes to load it. So due to read-ahead reads, like my SAN can keep up, and that ends up not being an issue. Does that make sense? Can you repeat that question, please?
So, before running your test on SQL 2019, you had 112 files, right?
Yeah.
So when you did it on SQL 2019, did you have the same 112 files?
So the question was, when I upgraded to SQL Server 2019, did I change any other part of the load process, right? The answer is no. I had the exact same 112 tables that were sourcing my data. There weren't any changes with that respect. So like the only change here is I changed my version of SQL Server. I am unfortunately in a virtualized environment, yes. So the question is, if you're in a virtualized environment, then why are you trusting perfmon? It works for me. I don't know how to answer that.
The answer is you're the only VM on the tenant.
Oh, okay. So the gentleman in the hat helped me out. I've got a 96-core physical host. And I've got a single 96-core VM on that physical host. So there's one tenant. There's no oversubscription. The question is, why have a VM at all? It's to make my 6-minute data load even more impressive. No, it is because my VM administrator will not give me a bare metal server. It's very sad. I've asked many times.
This VM administrator is not the man in the hat.
Yes, yes, that is true. Any more questions?
How about partitioning?
Partitioning for staging or a report?
Main table.
So the question was, would partitioning the target column store improve load performance, right? There's some trade-offs there. If you insert into a partition table, SQL Server has to figure out which partition your data is going to. And there's no way to do that without overhead. The benefit for scalability would be there's a row group flush lock taken as part of writing Delta, or as part of writing the column store, the row group. I believe that's at the partition level, so you could reduce that bottleneck, but I don't think I have much. Yeah, like, so you see the 16 seconds of lock MX wait, that's that row group flush. So for me, like, that's not really a problem. You could put your partitions on different file groups and maybe attack PFS contention that way, but SQL Server 2019, no longer a problem. So I would say partition your table depending on the size of it and how your end users are querying it, and make sure your load process is compatible with loading it. But the only really big benefit in terms of load is if you want to do parallel inserts, so max stop greater than 1, you can partition switch out your partitions and do concurrent parallel inserts. If you're doing max stop 1, if anything, it's probably a penalty. Does that make sense?
Did you say that you had this in simple mode?
The question was, you have a simple recovery model, and the answer is yes.
All the step is with a cluster Columnstore index or a non-cluster?
So the question is, what kind of column store index do you have in your target table? I have a clustered column store index with no non-clustered indexes.
And would it be a different all the step if you had the non-cluster instead of the cluster?
So the question is, would I see different load performance if I had a non-clustered column store on the table instead of clustered, right? So the answer is yes. It would be different. My guess would be it would be slower because now I would have a row store version of the data, which is 300 gigs, and I would have a non-clustered column store version of it. So I'd be inserting 300 more gigs of data than I was before. So I strongly suspect it would be slower in this case.
What if next view is not 1 but 8 or something? Because real world for the production SQL Server has more than 1 for the next view piece.
Can you repeat the first part of that, please?
So what if next view is not 1?
So the question is, what if my inserts have max stop greater than 1, right?
Next view is
For data loading, you mean, right? Okay, so I'm going to try to answer that. I have a max stop 1 hint at the query level because I need to do serial inserts. To do a parallel insert into a column store, you need a tab lock or tab lock X hint on the target table. So that doesn't allow for concurrency. So if I was doing parallel inserts into this table, I can only have 1, which means to be scalable, I need max stop to be 112. And I want to use max stop 112. Does that answer the question? No? Can we talk about it after the session? Okay.
You also don't get consistent row groups.
There are lots of problems with parallel inserts, and I've got a few slides about it. There was a comment about consistent row groups, and that is very true.
But force all the queries onto their own schedulers.
Sorry, what was the first part of that?
You force each insert onto its own scheduler.
So the question was, how do I force each insert on its own scheduler? There are a few different ways of doing that. One way of doing it is you change your store procedure to try to reserve a row in a shared table for that scheduler. So your application code checks, am I the only user work on the scheduler? If you are, then you reserve that scheduler, run your code and quit. If you're not, then you quit with an error code. The client calling that store procedure gets that error code, and then it knows, okay, I need to create a new connection for the store procedure. If you create a new connection, then you get another chance at scheduler assignment. Does that make sense? The question was, do I have hyperthreading on? I have hyperthreading on the physical host, but those hyperthreaded cores are not exposed to the guest VM. So from a SQL Server's point of view, there's 96 schedulers, 1 thread per physical core. So the hyperthreads would help for ESXi overhead and stuff like that. Okay, I have a few more slides. I'm happy to answer more questions. So quick review, loading a lot of data, make sure your inserts are more than 102,400 rows, and make sure your cardinality estimates are good enough. Got resource turnover weights, fix them. Increase max server memory, consider resource governor, consider concurrency, whatever you have to do. Page latch up. So figure out where the weights are happening, which database, which pages they're happening on, then address the problem. You might need more data files. You might need to upgrade SQL Server 2019. This is not an I/O weight. It's pure logical contention. You might have signal weights. If you see these signal weights and you're doing max up one loading and you're the only person on the server, if you want the best performance, forcing this behavior can be very helpful. Force each session to be on its own scheduler. It can make a huge difference. This weight. So I've done all the hard work for you. Lock pages in memory. Use it if you can. Load more rows at once. If you're on 2017, some CU and adventurous, use traceleg 876. Tell Microsoft about your experiences. Don't use 834. Okay, we talked about loading with max stop equal to 1. What about parallel inserts? So I hope you enjoy the royalty-free clip art I found. This is much harder than max stop 1 inserts. So if you were sitting in the session, you thought, yeah, I could do all that, no problem. Maybe you're ready for this then. Okay. So why would you try this? You might have many parallel queries on your server, and you just want to run nothing but parallel queries as part of your ETL process in order to balance your work a bit better. Maybe you have a complicated select part for your insert into Columnstore, and you want query parallelism for that select part. Maybe you've got skewed sources of data. Say you have 10 files. One max stop, one insert per file, that's not going to work out too well. So there are reasons to do this. If you want the best possible scalability, it is very hard to do. So you have pretty much all the problems we talked about before, and then some new problems. So new problems. On 2017, SQL Server can downgrade your max stop based on what it thinks it needs for memory. And what it thinks it needs for memory for compression can be much, much higher than what it could possibly use. The workaround is use the default workload group. I don't know about you, but if I have resource governor turned on, I send all my work to the default. You might have poor performance of the select part of the query. So the parallel insert gets a memory grant. That memory grant is shared between the select part and the insert part. The insert part is very aggressive in how much memory it asks for. And the select part operators can get starved out. It's very easy to see the select operators or the operators as part of the select tree executing with the minimum operator grant. So that's 1 kilobyte per DOP or so, depending on the operator. That's very bad performance. The workaround for this, take your select query, insert into a temp table, then insert from the temp table into Columnstore. So you can do 2 loads in one. There are bugs where depending on what you do, your query will run forever. Now, I can't prove that. The longest I waited was about 72 hours. But 72 hours, not using any CPU, it's not good. So patch your SQL Server. If you're using Columnstore, patch your SQL Server. It's very important. Columnstore is still pretty new. Microsoft is making improvements, sometimes bug fixes. Get those CUs. If you don't, your query's going forever. That's pretty good incentive, right? Okay, so sometimes the internals change with CUs, even though Microsoft says they won't. There's a hard-coded memory graph, 25 seconds for Columnstore inserts. It's not based on the configuration. It's not based off of the query cost. If you hit that 25-second timeout, bad things can happen. And the flavor of bad thing that happens depends on your CU, on your max stop, on how much memory you have. Like in some cases, you can get concurrent worker threads where the same query all running to Delta stores. It can deadlock. You can exceed your target memory. All kinds of bad things happen. So you remember those resource semaphore waits I said were horrible? Avoid resource semaphore waits with Columnstore. If you want to be as scalable as possible, you want to use each and every CPU, you need to be doing useful work. The allocation strategy for parallel workers is very simple. It's round robin by soft NUMA node. So there's some patterns of work where you can see schedulers doing nothing and schedulers doubled up and tripled up. Disabling all soft NUMA can help. On large servers, I have a blog post explaining that. There's documented trace lag 2467. You're welcome for that, by the way, which also can help. That changes the allocation algorithm to try to pay attention to how busy the NUMA nodes are. Yes, that's correct. By default, for parallel worker placement, SQL Server does not consider how busy your soft NUMA nodes are. It just goes round robin. There's a latch called nesting transaction full. This latch is required for parallel inserts in the heaps or columns or tables. This can be a big bottleneck depending on what type of data you're inserting, how much work there is to insert per row. So this is a reason why going above max stop 8 for the most part for parallel inserts is not a good idea. You eventually hit a wall with this latch and your query speed doesn't get any faster. I've got a blog post about this. There is no workaround except lower max stop, but who wants to do that, right? That's it. Thank you so much for your time and attention. Enjoy tomorrow.